Can you all see my comments and stuff on your lab report? One thing that you might need to do to be able to see it is in the assignments area. If you go to the files, don't just try to preview it. Okay, if you just try to preview it, you will not see my comments. If you do need to see my comments, then you have to go to the files area, and you can't just download your file. You have to download what it calls annotations, because my comments a lot of times will be sticky notes or highlighter or various things on the paper itself. Okay, so download the annotations to see the stuff that I'm saying that you need to fix. So some of the problems that I talked about before, like a lot of times your conclusions do not match your graphs, do not match your equations. It's like you're talking about somebody else's data. Another big thing, and I think this was still in the one that you sent me. I think y'all still talks about the solid to liquid transition. And looking at your graph real quick, I don't see a solid to liquid transition. I might see a liquid to gas transition on your data. But I don't see a plateau down at 0, which is where your solid to liquid transition should be. Does that make any sense? Does it even make sense what I'm saying? Okay. When you're doing your data, right? So you got your T over here, your temperature over here, right? And so at 0 C, we started down here somewhere, you should so this would be what phase is our H2O right here? Solid. What phase is it here? Okay, well then this is the solid to liquid transition. Does that make sense? This one up here is not that. This is still a transition, but it is a liquid to gas transition there. Okay, so make sure that's the sort of things I'm looking for. Those are like idea level. They're a bigger deal than whether you calculated something right. Making sure you get the concepts in. Let's see. Other questions going on out there? Who's got other questions? I was talking to Allison about she's not getting bombarded with a lot of homework questions right now, so I assume that's good. Assume that means y'all are dealing with the homework okay. Although Murphy now says he's going to yell at me about it, so I don't know. So, how was the homework? Okay.
I spent all day.
Oh my God. No. And I would expect this to be, for me, 15, 20 minutes. So for you, an hour-ish. Does that make sense? 15, 20 minutes to, and I mean, and I'm not just like shooting in the dark. I actually, I do it too, right? So I'm actually laying it out step by step also, and that's what takes a lot of the time is structuring it, laying it all out and stuff like that. Okay? Allison, you have this one already? Remember when I did that? You already have that? Okay, cool. What else we got going on, y'all? Anything? Lab today? Yes? Yes, absolutely. It's a good question because I was going to bring up, remember last week. Last time we had a lab, I said that I didn't want to hit you with a quiz first day, right? But I do want to hit you with a quiz today. So that was an excellent question. I went, yes. For quizzes, it's open notes. Okay, so I am cool with you not bringing up your computers, but any notes that you have is fine. Okay, so and definitely your cheat sheet is fine. Your calculators are fine. Okay, I'm not gonna go in and edit the quiz today. I handed it out Thursday night and realized that the first question on it is actually going to have to do with what we're doing today. So the first question on it, I'm not going to grade or give you any feedbacks on. Okay, that's probably a big hint, but I'm just going to hand it out as is. There are 4 questions. I'm going to grade the last 3. Okay. All right. Other questions. So, okay, I guess we'll go on. We'll get into the meat of today. Y'all let me know. We'll be in live this afternoon, so for any more questions there. Okay, thought experiment to start with. I have a table. We're going to use Murph's table here, okay? So, Murph, you're helping us picture right here the thought experiment I'm about to set up. You can just do this in front of you or think about Murph's table up here where I'm going to be pointing, okay? All right, now on this table, a little block of ice, kind of a big block of ice. Okay, so we got this big block of ice. Now, if the table weren't here, what would the block of ice do? Why? Why would it do that? Why not? All right, everybody process this for a second. I have a reason for asking such a weird question. So, Murph, you're saying if the table weren't there, what? Then it would fall and get to the ground. Yes? Everybody agree with Murph on this? Yeah? Okay. All right. All good. You're picturing that. Yes? Well, now wait a minute. I want to zoom in right there. You see I've got a corner of my block of ice hanging off of that, right? So it's falling to the ground?
No, it's not.
Wait, why?
Because the ice is center of gravity is not.
Well, okay, but what's going on with those? Let's see. This is the crystal structure of at least one version of ice. I'm going to talk about different versions of water ice in a little while, but the one that you're most familiar with, those red and white sets of spheres are supposed to represent water molecules, the red being the oxygen and the whites being the 2 little hydrogens stapled onto them, right? So they're sitting there in this cubic, well, it's actually hexagonal. It's a hexagonal structure. Okay, Murph, you said if the table weren't there, the block would fall, yeah?
Yes.
But the table it does not actually extend underneath that little water molecule right there, does it? Well, why is that little water molecule not falling down? How is it connected? Is it got like little handles? Little hooks? That's actually a reference to chemistry history. Okay. All right, hold on. Let's go back to the big block. Now, in physics, what do we say has happened to the block when it starts to fall? Come on, I know you saw this in like middle school business, right? What's it going to do? Why does it fall? Why does it not just maintain its zero momentum state? There is a force called gravity is acting on it. Okay, everybody agree with that part? But what? There is still the same force of gravity acting on that water molecule that I've got the laser pointer sitting under, right? The force of gravity is still acting on that water molecule individually, is it not? Then why is it not falling? Why is it not starting to accelerate? Thoughts? In physics, when does a thing accelerate or not accelerate?
Forces are not equilibrium with each other.
Do y'all understand what Braden's saying? Say that again, Braden. Let's make sure everybody follows what you're saying. You're right.
When there are forces not equilibrium with each other.
So if there's an unbalanced force, right? Now here, acceleration appears to be 0. We can just sit, watch it, and wait, assuming their room temperature is enough that it doesn't melt, right? It'll never start to accelerate. Its acceleration must be 0, right? That implies from what Braden said, that we do definitely still have, y'all agree we still have force of gravity pulling down? I mean, if we don't, if that changes, a lot of things are broken. But I'm gonna assume that, yes, we do still have gravity trying to pull that thing down. Then what must be true here? From Braden's, let's dissect Braden's argument here. Go ahead, say it again. Equilibrium. Net force equals zero, basically, is what you said.
Yeah. But there's not any acceleration, then force in the object has to be zero.
So, but we know we've got a force down. What does that have to tell us?
Gravities.
Okay, start with the first part of the sentence. The connections between the molecules. Hold up, what did you say? That what?
That force is supposed to be equilibrium.
But there's a force pulling down, connections between those molecules, dotted lines. Must be, and must be forces. Right, that's what I'm getting at. And a lot of people don't think of the micro scale like chemists do, where we're actually picturing what's going on with the little molecules. And here, I am claiming that there is an actual force being applied by the adjacent water molecules that are counterbalancing the force of gravity. I do think that the force of gravity is still there. I just think the net force has gone to zero because it's canceled out by what we call electrostatic forces from the other molecules. Okay, that's where we're going today. Well, now our situation has changed. The room has warmed up. What's happening now? Agreed. Now use our new stuff about forces to try to talk about what must be going on here. Yes, the ice melted. Yes, that's a macro description. Let's go down to a sub-micro description of what's going on. Say it again. That's true. What else? Sub-micro, zoom in. Zoom into those little diagrams, right?
The water doesn't have that strong.
Oh, very good wording. Say it louder, Murph.
Water doesn't have strong forces.
Okay, so now I'm going to make some claim from this thought experiment that we're going to change the degree of forces such that, well, now they're not strong enough to resist gravity, and it will fall. It will start to accelerate. Does that make sense? But we're not done. It hits the floor. Let's say it's not carpet. It's a nice, well-polished tile floor like in the lab, right? And we get down, real close, zoomed in. What do I see? That drop of water that hit the floor. What does it look like? What's it shape? Yeah. How about a 3D shape? Yeah, like a deformed sphere. It wants to be a sphere, but it's not a perfect sphere because it's sitting on the ground, right? And it turns out different liquids are differently a difference in how good they are at making a sphere. If you drop mercury on it, it will actually make a full sphere, almost, right? Whereas if you drop water, it tries to be, but it pretty much smushes down to a half sphere, right? And different things have different angles that they do. But here's what we got. But it turns out that the force argument is still going on. Why? Why is it making this dome structure? What's going on with that? Well, I'm going to claim that there are still forces between the individual molecules. They're not as strong as they were in the crystal form now. There are still forces, but the ones on the outside, look at their force diagram there. They got forces to all the folks that are surrounding them. Oh, but wait, there's a direction where there are not any guys surrounding them. So there's no force pulling them that direction. There's still a net force pulling them all together, right? That really describes what's going on in the liquid. I think we've got to get a little deeper on that, but that really describes what's going on in a crystalline solid, in a liquid, and then the absence of that is what describes a gas that we did last week. Okay? That make sense? We're gonna get a lot of crunch here, but conceptually, do I give you a framework now to layer all the stuff that we're gonna go on? Any questions about this so far? All right. All right, gases, liquids, and solids. So tell me, middle school version, your little sister in middle school asks, hey, you're taking these college science classes. Miriam, help me out here. How do you tell a solid from a liquid from a gas? You'll be ready for a test tomorrow. How do I tell? A little, like a middle school kid, maybe like.
A solid can hold its shape and the molecules are compact.
Okay, keep going.
And then a liquid, the molecules are like less compact and they take shape of whatever container they're in.
Ah,
And then a gas is like floating like free particles and having space.
good. Somebody read. Yeah, good. All right, so my typical thought experiment on this, to make it lock in, I used to use this a lot with my physical science classes, 8th, 9th grade physical science classes. All right, consider a cube. Okay, we have a cube, and it is 10 centimeters by 10 centimeters by 10 centimeters, right? 1 cubic decimeter, which, by the way, is the definition of a liter. So this is a 1 liter cube shape. Does that make any sense? Got this container. It's got an airtight lid. It's the shape of a cube, right? And it's exactly 1 centimeter, 1 decimeter, with 10 centimeters on a side, right? Okay, cool. At first, I have in it a cube of iron. You ever played with a cube of iron? Okay, so I have a cube of iron. Open the lid, yeah, and I dump it out on the floor. Good? Probably true. Now, here are my questions. Here are my simplified questions. One, so it was a liter when it was in the container, right? Is it still a liter?
Yes. I agree.
Is it still a cube? Yes. All right, cool. And we claim that because it is a solid at the temperature. Let's assume we're at room temperature. Okay? Now, new time, come in with the same cube. This time it is filled with H2O, right? All right, I have a liter of H2O, right? In the shape of a cube. Yes? Open the lid and I dump it out. Is it still a cube? No. Is it still a liter of water? It's just spread out, but now there's a liter of water on the floor. Does that make sense? We claim this because it is a liquid. All right, new experiment. What was it? Axe cologne, you said? Is that what you, okay. So we have Allison's Axe cologne trapped in this 1 liter cube, right? Yes? All right, I'm gonna open it up, dump it, well, wave it around, whatever, right? Is it still a cube? Not exactly. What shape is it? The root, which is, it's not exactly a cube. But definitely, is it still a liter? No. No, it is whatever volume this room is. It spreads out to fill the new volume, whatever it's containing. Does that make sense? Okay, so here's what we're going to say is that a solid maintains its shape and volume. A liquid maintains its volume, but not its shape. And a gas maintains neither. Very simplified version. It's actually a lot more complicated than that, turns out. But I wanted to reinforce that real quick, make sure you got that version first. Okay? Any questions before I take this nice simple model of your world and break it? Because I'm going to. Okay. Ready? Anything on this before we get deeper? All right. I haven't mentioned plasma yet. So, typical high school version, they tell you that there are maybe 4 states of matter, right? Solid, liquids, and gases, and then they add this other one, plasma. And I just wanted to make sure that we do not think that plasma is somewhere in between. Where is it? People thinking? It's in between liquid and solid, maybe? Is that what they think? So the misconception that I see a lot, and it is not. Okay, a plasma, so these are arranged from bottom to top in energy levels. So if you take a solid and apply a lot of energy, it gets to be a liquid. You apply a lot more energy and it gets to be a gas. And you apply a lot more energy than a gas and it gets to be a plasma. Basically, a plasma is a gas that has so much energy that its outer electrons start to get stripped off and it becomes an electrically conductive gas. Okay, just making sure. You should have probably already heard of that in high school. That's okay. Now we talked a lot about gas last week and the week before it is. What do we need? It has no definite volume, it has no definite shape. We can change that. And we're going to do that in today's lab. We're going to be playing with those gas laws from last week. We're going to be compressing, measuring temperature, measuring pressure, volume, all those things with our gases. So we're going to kind of get a hands-on version of the gas laws today in lab. All right. I want to mention that later I'm going to talk about fluids. And so for the four that we have, the four states of matter that we've considered so far, everything but solid is going to be considered a fluid. A fluid just means that we can mush it around. And remember, I'm a geologist, so I have to add a caveat to say we can mush it around fairly easily, right? Because you can actually mush solid rocks around as a geologist. It gets a little more complicated when you get high temperatures and pressures in the center of the earth and stuff. So, all right. Okay, we did talk about this. Basically, it's just more text to go with the same idea. Okay, solids. Now I get to start breaking things. All right, let's think about that solid. How do we define a solid? So it holds a shape, okay? And we use the iron cube as the example, right? Yes? But I take that iron cube to my anvil. And I really go at it with a hammer. How well does it maintain its shape? Can I change its shape? Oh, well then what does that do for us? Does that break my definition? Would you agree that the cube of iron is in fact solid? I would too. So I'm not changing that on you. Good, right? I'm just saying that the real reasoning gets a little deeper than what we've gone with so far. That was kind of the high school version, right? But the real reasons are deeper than that because the solid resists a change, a deformation of shape, but it can't resist it entirely, right? Okay, for example, how many of y'all are biologists? Yeah, okay, all right, a lot. Okay, so tell me the idea between endothermic and exothermic in biology, or warm-blooded, cold-blooded. What's that? What's that about? What is warm-blooded and cold-blooded? Some animals are warm-blooded, some are cold-blooded. The homeostasis idea that they do what with heat?
Like they, let's look at that, either absorb it, like they contain it, or they release it.
Yeah, so what I heard was that warm-blooded animals can maintain their own body temperature, cold-blooded cannot. Right? Is that right? This came up a lot when I was studying some paleontology stuff about dinosaurs. Right? I remember back when most people believed that dinosaurs were entirely cold-blooded. I'm that old, right? That means that I'm this old stuff. I am old enough to remember when everybody thought of dinosaurs as entirely cold-blooded. And I remember Robert Bacher producing a thing in the 70s called Dinosaur Heresies, where he initially claimed that dinosaurs might have been a little bit more blooded. Now it's pretty well accepted, but then it was not. Okay, so warm-blooded animals can maintain their body temperature, and cold-blooded animals cannot. That's the claim, right? Which one are you? Which one are you, Brady? You're a warm-blooded? Okay, but I would claim things are not that simple. If we drop Braden off in Antarctica in his Speedos, he's that warm-blooded. He's not gonna be able to maintain his body temperature, right? And maybe actually we had some difficulty maintaining your body temperature last week in our local environments, right? Yes, it was pretty rough. So maybe the world is more complex than this high schoolification that we do, where it's called a concrete idea, concrete and abstract, right? And so we say things are warm-blooded or they're cold-blooded, and the real answer is, well, ish. That make sense? So a lot of your college chemistry class, especially Chem 2, we're going to get into this ish idea. Okay, so now we're going to need to look for a new version because solids can resist a change in their deformation, but not perfect. Okay. All right. Anything else? So then a lot of talk out there on the internet about this. You seen it? What have you seen?
It's gas.
It's glass a liquid. What have you seen about it? Has anybody seen any of the memes or YouTube discussions? Where else? This is a YouTube discussion right here. What else? Anybody? Anybody ever seen this? Nobody's seen this. You have? Where'd you see it? Just like randomly?
Yeah.
Okay.
There's people that like, old stained glass.
Okay, old stained glass. Y'all never seen this about the old stained glass windows? Nobody has any idea what me and Mark were talking about. Sometimes this happens. All right, try to explain to them, man.
So there's people who claim that like old stained glass seems to be.
First, you know what stained glass is.
Yeah.
All right,
The structure is real old, usually been glass for a long time.
hundreds of years.
So it looks like this glass is like dripping. So it's like, how can you do that to solid? So these claims that glass is still liquid. It's solid.
Y'all feel where he's going with that? Okay, so a lot of these things out there on the internet like that, and I don't want to say, this one's not really a conspiracy theory, although this argument will apply to a lot of the conspiracy theories out there, have to do with people not getting far enough into the science. It's actually clear, glass is clearly a solid. Okay? It's just that they haven't gotten deep enough into it. Now, there's also some debunking the idea about the glass flowing down and being wider at the bottom. It's in this video. If you're interested, the video, it's really fun to watch. It's actually a good one. But it is a solid. It's just a glass. That's another version of solid, right? And so I would claim that it can, even though it can deform over time. If you set a piece of glass, and we're talking about non-tempered glass, okay? If you set a piece of glass here off the edge, right? You leave it, well, if you just watch it, nothing happens, right? If you leave it for hundreds of years, it will in fact sag, right? It won't maintain its shape perfectly, but it maintains it well enough. That thought experiment we have to start with doesn't just drip, right? So we need to look a little deeper for evidence. Now, I've broken the simple high school definition of what's a solid, what's not, right? So now I need something deeper. So what we do is we actually analyze, I think that's my next slide. We actually analyze these things. Okay, I'll come back to that, I don't know what's on it. We'll actually analyze these. And so we can see changes in the actual characteristics of a material, and we can see these spikes down or up. This is a temperature of crystallization, and this is a temperature of melting. So we can see different things happen to the material when we really carefully measure what's going on. Okay? And so now we're getting a lot deeper into what's a solid, what's a liquid, what's a something else. And there are different kinds of solids. All right, let me ask that. How many of you have ever heard of different kinds of solids? You have? Anybody else? Murph, what have you heard of? Amorphous versus, this is a big division, is amorphous versus not amorphous, but, so the geode that your mom picked up at Vesuvius has what in it, little what's? Amorphous versus crystalline solids. That make sense? Okay? All right. Polymers, wow. When you get into polymer plastics, they break the whole system even worse. Okay? Yeah, yeah. And the whole, is it a solid? You know, you think like that happens, right? This happens to me. So like in middle school, I had no idea what a chemical bond was, right? And then taking undergraduate classes, yes, I learned what a bond was, right? And then upper level, undergrad to graduate level, now I don't know what a bond is anymore. So that happens to you. Yeah. So that kind of thing happens in science a lot. So yeah. Do I want to talk about this one yet? Okay. So another thing that happens a lot is I hear conflated. You all know the term conflated? What does it mean? Put together, like used synonymously when it may not be synonymous, right? So I hear people use the term phase interchangeably with the word state. Phase of matter, state of matter. They're not the same thing. So there is some finite number of states of matter: solid, liquid, gas, plasma, Bose-Einstein condensates, neutron star matter, the other kinds of degenerate matter, stuff like that, right? There are an infinite number of phases of matter. So let's think about that for a second. Let's try to figure out what distinction I'm trying to make. Anybody like oil and vinegar salad dressing? Sydney does not. Why, Sydney? Guess what?
Doesn't taste good.
I agree with you. What does it look like sitting in your fridge?
Weird looking separated.
Separated. Now hold on. It's separated into what? So you got two different areas. You like that's your jar you were picturing. Tell me about that.
Oh, I think like the oil, like some top and the rest of the bottom.
So when okay, that oil that's on the top, what state of matter is it? It is. So that's only well, okay. Well then, what state of matter is that stuff below it?
So,
Oh wait, both of those are liquid states. You agree? However, I'm going to claim that they are separate phases. Does that make sense? That's an example of what I mean by phase. You can have multiple liquid phases. When I did a lot of environmental work, I did a lot of chasing groundwater pollution in aquifers, and we would talk a lot about LNAPLs and DNAPLs and dissolved phase. So an LNAPL, it's an acronym that stands for light, non-aqueous phase liquid. So it's a liquid, right? Let's say you've got a diesel tank underground and it ruptures and the diesel fuel leaks out, right? You've got groundwater down there and the diesel fuel will sit on top of the groundwater because it's lighter than, it's less dense than the water phase. And so it's still a liquid, but it's a light phase, so it'll separate and be another phase sitting on top of the groundwater. Some will dissolve in the groundwater too. There'll be a dissolved phase too, but you get separate phases. Now, if you get something like a creosote, I did a site in Gainesville, Florida, where we had creosote in the groundwater. It's kind of like a coal tar. It's harder because it's a DNAPL is what they call it, because it's a dense, non-aqueous phase liquid, and it actually sinks to the bottom. That's harder to get out. Different phases. We'll talk about different phases. Yeah, that's the same. Okay. All right. About to go to a deeper piece here. So let me back up, slow down for a second, and listen to you. Where are we at on my discussion of phases here? Does it seem like it makes some intuitive sense? I need to hear from you on this before I go to phase diagrams here. Yes? You feel okay with it? Okay? I'm asking this because I'm about to go deeper. Okay? I want to make sure and solidify where we're at. Feel good with it? All right. Okay. I mentioned that I was only talking about one of the flavors of solid H2O. We're going to talk about multiple flavors. So there are different kinds of solid phases. This is what's called a phase diagram. Okay? It's a phase diagram for the H2O system in pressure and temperature. Okay? So anybody do a lot of cooking or watch cooking shows or anything? Yes? Yeah, okay. All right. So do they talk about in your cooking shows, do they talk about boiling and depending on where you live? Yes? What do they talk about?
It also affects baking temperatures.
Why? Because the guy said it, but
Yeah.
let's go deeper.
Because there's different air pressures, like depending on the sea level.
Yeah, keep going.
It also depends on how high or low you put,
Why?
because there's more, like, I don't know if I'm getting mixed up with more air pressure up here.
Yeah, the other way around. Yeah, there's less air pressure in Denver than here, right?
Because there's less air on top.
Yep, less air pressure down here. Okay, so this is going to be a claim then that pressure, which is my y-axis on this diagram, it doesn't have to be. You can set these up any way you want to. But right now, a simplified version is going to have pressure on my y-axis, okay, and temperature on my x-axis, okay? Now, I warned you before that I tend to graph things and I tend to think of things spatially, right? So this is one of those examples. I tend to lay things out, and a lot of chemistry does, tend to lay things out in a graphic orientation so we can see where things are. I am looking at these different zones. Some of them are color coded, some of them are not so clearly done, but I'm looking at these different zones delineated by the red lines on this graph. They talk about different phases of H2O, okay? Now, here, in this area, that phase is also a state of matter, but that's not always going to be the case. In this area down here, this vapor phase or gas phase is also the state of matter, gas, okay? So far, so good? And this, I don't know what to call it, maybe that's greener zone is the liquid phase. See how it's separated by that red line, okay? Now, here, this is the ice phase where I'm pointing here, the 1H solid phase. This is the kind of ice that you are familiar with. It floats in liquid water. It, for the most part, freezes at 0 C, stuff like that. Okay? So far, so good? But then you notice these other Roman numerals, these are other phases, other versions of solid H2O. Ice 11, you've got ice 7 and ice 10 up there. that exists under these other conditions that are defined by the pressure and the temperature of this graph. Does that make sense? So far, so good? Yeah? So, anything else you see on this graph that I got another slide of this graph. You want me to clarify before we give an example? Okay, give an example. So, what temperature are we currently at? In this room, yeah. What temperature were you saying we were at? Oh, no, you're in apps, aren't you? Yeah. Gotta convert for us. I believe. I'm not gonna go check. 25C, but wait, you gotta convert also because. Okay, about 298. All right, so we're at about 298K. You agree? Okay. What pressure? 1 ATM. Let's see. So that, do you remember the conversion to pascals? It's about 101 kPa. Okay. Yeah, so about 100 kilopascals. So turns out that about right there. It's a logarithmic graph. If you have trouble with a logarithmic graph, it's not something you need to know for this course, but I'll gladly help you with it anyway. But just if you look at the scale bars, you'll see how it's zoomed out. It zooms each time, each spin. So we're about right there. And about 298K. And so what I would do is if I want to know what phase something is at a certain pressure and temperature, I use a graph like this and across the X and the Y, right? It's just like plotting lat and long on a grid, right? And so at our temperature and pressure, if I have a sample of H2O, what phase would I expect it to be in? Liquid, because we're in the liquid zone on the graph. Does that make sense? Okay, good. All right. A couple of other things to point out. If I had, let's say, like about right, what do we got here? About 100 megapascals, okay? 100 million pascals, so pretty high pressure, right? And let's say 900K, right? Follow me? Follow where I'm looking at? What phase would you expect H2O to exhibit there? Why? Is it? Are you sure? Well, but look at what happens to my nice solid red line. Divided vapor and liquid, what happens to it? Yeah, and that's a really good description of it. How many of you have ever heard the term, sometimes it's thrown around in the news or something, supercritical? This is what's called the supercritical zone for this system. And out here, when you get up there in that zone up there, use the laser pointer again. When you get up here in this zone, we get a fluid, we're sure of that, but whether or not it's a liquid or a gas, we cannot be sure. We lose distinction of what a liquid versus a gas even means up there at those pressures and temperatures. You can't tell them apart. So there's called a critical point, that last little red dot out there, the last point we can tell. And then all those dotted lines coming off of it are what different people think. Different researchers look at it differently. Well, no, I'm sorry, that's wrong. These green lines appear to be density grams per cubic centimeter. But there are other lines that you can find out there where people are guessing as to what the behavior is out there, but that's a supercritical. And where this is coming home right now, current research, one of the big problems in chemistry is the solvents that we use, and they create a lot of contamination, right? And so a lot of people are talking about using what's called supercritical CO2. So doing your chemistry experiments, and you take carbon dioxide, cool it, and put it under extreme pressure, right? So you can get it to be liquid-ish, right? And you do your experiments in that, right? And when you're done with your experiments, when you open the lid, you have no solvent to worry about because it's all gases. That make sense? So anyway, supercritical CO2 experiments are a thing. All right. Yet another phase diagram. I love this one because I'm a geologist, right? Anybody have a, don't tell us any names, but anybody got one of those hate friends that loves showing off the bling, right? Got a nice diamond ring, right? So just so you know, you should never, ever take that person's diamond ring and put it in an oven because James Bond notwithstanding, diamonds are in fact not forever. Diamonds are actually not stable at a temperature and pressure that you're currently sitting at. What's the chemical formula for diamond? C. It's just carbon. What's the chemical formula for graphite? C. It's just carbon. In fact, if you heat that diamond up to what's called a activation energy, right? Critical temperature, it will revert to its stable form. And your little hate friend will now have a graphite ring. Please don't do this, right? So this is a phase diagram for carbon. Here we have temperature again and pressure again, just like we did. However, please note the difference in scale here. Pressures on this diagram, this is a geologist type diagram, and pressures are in gigapascals. Okay, so really ginormous. Yeah, really ginormous pressures, right? Also, these temperatures are quite high. Okay, in kelvins, but subtract 273, that's still quite high. Yeah, okay. So we have these different forms. Well, we got liquids. Now we have two different versions of carbon liquids. See that? So there are two different phases of carbon liquids here. And also we have graphite phase and a diamond phase. And there's their structures up top. So it turns out that diamonds are stable close to the core of the Earth where you have that super high pressure. Graphite is what's stable at our pressure out here, which would be our pressure is almost on the x-axis, it's so low down here, okay? But very, very low pressure graphite is your stable form. Does that make some sense? Okay. Yes? Allison, you think of anything I'm missing on this? Next Wednesday, the lecture is phase diagrams, so there'll be plenty more on phase diagrams.
Learning this for the first time, but how it is. So you're defining phases as being dependent on temperature system.
Well, in the examples I have given, those are the two axes. Let's go back at the definition. Yeah. So defining phases is actually a little difficult. There's an official textbook definition here. A homogeneous substance with a well-defined set of physical and chemical properties. Probably a more accessible definition is, like I said up here on the slide, I can't guarantee you that this will always work. This is just kind of my made-up version of a definition. But I want to think of it as something that is physically separately. You don't need a chemical reaction to separate. Okay, so Sydney talked about the oil and water phases in that salad dressing. They separate, right? So those are physically separate. Or my El-Napple in a groundwater, I could go in and dig a hole, right, down to where the gasoline is sitting on top of the water. I've done this and suck the gasoline out without having to suck too much of the water out, right? Because they're physically separate. Does that make sense? Does that help? What were you gonna say?
I just have,
Anything else on this? Keep going, please. They're not asking yet, and I want them to. Is anybody sending her questions? Remember, if you don't like to ask questions, if you don't want to put yourself out there, Allison will ask them for you. She doesn't mind. Okay, all right. Anything? Nothing? Okay, you just throw in when you need to. Stop me when you need to. Y'all send her a message. She'll stop me and maybe go back or whatever. Okay? All right. All right. Next thing, this is a giant thing from Chem 2. One of the big learning outcomes from Chem 2 is this IMS, intermolecular forces. Oh, all right, IMS. So, anybody in here play intramural sports? You do? What? Intramural or intramural? Well, no. Let's talk about that. Tell me what you think.
Let's say intro.
Okay, well, what's that? You play intramural basketball? So if you're playing intramural basketball, does that mean you're going down to play Georgia State? Wait, why not?
I'm not that good.
Oh, wait, okay. So intramural basketball. Allison, you used to play intramural volleyball? When you were playing volleyball in high school, right? What did y'all go play against other schools? Okay, so that's inter, right? And yours is intra. What's the difference in meanings? Help me out here using the sports analogy. Sports ball analogy, come on. That's okay. You can help me clarify now.
So they're playing people
Within their college.
So it's like a scrimmage, like if you were to have like your, varsity and JV team scrimmage or something.
Okay. When I was at Georgia Tech, we had intramural football, right? Now, when you play intramural football at Georgia Tech, you got to get out on the football field, right? And full pads and everything else and play against other people from Georgia Tech, which was a lot less painful than the people that played intramural football and got to go play against those people from Athens, right? Does that make sense? They're really different worlds, right? I could probably play intramural stuff, definitely not intramural. Y'all see the difference? Y'all follow me? Okay. Same thing here. Keep that idea here when we're talking about intermolecular forces versus intramolecular forces. So what am I trying to say? What do you think? Extend my sports ball analogy and tell me, what does it mean? Intermolecular versus intramolecular forces. Within a molecule is which?
it's,
Intra,
inter is,
attracted to other molecules. Okay? So those forces that were holding our H2O molecules to the rest of the block of the ice in the original thought experiment are which flavor? Which y'all think? What do you think? Inter? One.
Because it's various molecules, so just.
Yeah. Okay, Merv, what flavor of this is holding the hydrogens to the oxygens?
that's intra.
That's intra. Does that make sense? So it's H2O, right? Each molecule is H. It's two H's stuck to an O, right? And the intra molecule, the red up there, the intramolecular forces are holding the H's onto the oxygen. The blue one up here, intermolecular forces are holding one water molecule close to another one. That make sense? Okay? All right. So, right here, they are electrostatics. Okay? So now we got to get into the physics realm a little bit more. How many forces do we think there are in the universe? Not a single answer to this, but there are several good answers. 4. 4 is the most common answer you're going to get in physics. Some people claim that those are 1 or 2 different forces with just some differences in the DDQs and how they work out. I think the simple version, though, is for us to say there are 4. And what are they? Strong and weak nuclear, which you will probably never encounter. Gravity and electromagnetic or electrostatic. That's your 4. That's your only 4 options. Okay? So magnetism, electrical, all those things are all lumped into electrostatic. Okay? Yes? All right. Here's a word that I want to drag back out from either high school or Chem 1, hopefully. What does this mean? IMFs are non-covalent forces. What the hell does that mean? What's that word, covalent? Been a while? Yeah. What's covalent? Where is that? Where have you heard that term used before?
Chemistry.
Yes? Can you be more precise?
1, 2 gases.
Okay, yeah, I see where you're going with that. So covalent bonds like O2, right? Oxygen has a covalent bond between them, right? What does that mean?
Oh, is it that they share?
Yeah, it's the shared electron bond. Yes, yes. Does that make sense? Turns out those are really, really strong compared to the non-covalent. That makes sense? And that's what's going to be important is how incredibly strong covalent bonds are and that IMS are not those. And they're not as strong. Okay? Okay, kinetic energy. Now, we've talked a little bit about the relationship between kinetic energy and temperature, but let's look at what it does with these different states or phases. We can use either term here. What happens? So you got a solid, right? And remember, if it's not at absolute zero, then your particles do have kinetic energy. They're bouncing around a little bit, right? But they're not getting loose. They're bouncing around, but they're staying in their spot. Does that make sense? Right? Yes? Make sense? So middle school analogy. Again, I love using my middle schoolers as analogy, right? So middle schoolers are never actually still. Right? They're always bouncing around a little bit. But you can have a fairly controlled situation where you actually have most of them in their seats, staying there, not stabbing little Johnny with scissors, just, right? Does that make sense? But they are moving. There's going to be movement, right? They're moving, just hopefully not very much, right? But as you increase the kinetic energy, what happens? Right? They start to get loose from their spots, right? And move around, right? Does that make sense? Yes? Right so far? Yeah? If you increase the energy enough, right? If you drop a fairly large scale bomb under their school, right? Then they actually become airborne. Right? Does that make sense? If you add enough energy, like a nuke, you can actually get them to a plasma state. That's okay. Yeah. Is that good?
That came from.
Having middle school economics. Right, so anyway, the idea is you take a solid and you increase the kinetic energy, you can get to a liquid state. You can increase the kinetic energy more to get to a gas state. That's what I'm trying to show you. And the intermolecular forces still exist. It's just that as you get further away, right, the attraction decreases. Let me put a map up. Let's see, this board is ready. So, while it's getting ready. So, you think about gravity, how much gravitational force does the moon have? A lot, right? About what, an eighth of the Earth's gravity? I think that's right. Sure, that's right. Some significantly less than the Earth, but we're still talking about a lot, right? Yeah. But do you know that if you're not right on the surface of the moon, it's a lot less? Right? What does that mean? It means that your force due to gravity is equal to some g constant times your mass, the other mass, divided by r, distance from the center of those masses, squared. So the idea is that the force applied decreases with the square of the distance away from the center of the moon, right? So as you get further away from the moon, a spacecraft flying near the moon gets pulled into its gravitational orbit, right? But a spacecraft flying around nowhere near the moon can pretty much ignore that because the force applied decreases to the square of the distance. Does that make sense? Okay, same thing with our electrostatics. It decays with the square of the distance also. So as you get, so the IMFs are still there, but as those molecules are starting to bounce and get further away, when they're out here further away, that's when they can get loose because the force holding them together has decreased with a square function. So that's why they can start to slide around because they're loose for a little while, pull back, loose, pull back. Here, they've gotten so much energy that they're all the way free, not attracted again. Okay? All right, yeah. Yeah, you ready for this? Been looking forward to this one?
Yeah.
Okay. All right. We have three different types that we're going to talk about of IMS. In order of increasing strength, dispersion forces, dipole-dipole attractions, hydrogen bonding. Okay? And one of the big things that you'll see a lot on standardized tests, like MCAT or something like that, is this idea of hydrogen bonding. Okay, and how much it affects our world. Biology peaks, probably why life exists at this temperature on this planet. Hydrogen bonding. Okay. I wish that I had thought to mention last week about going back to review your geometry and polarity stuff from Gen Chemistry. We're going to need it now. So if you have not brushed up on your geometry and polarity stuff, you want to do that. Okay? So think about this. What am I trying to show up here? Let's just zoom in on one of these guys right now. What have I got right here? Chlorine attached to a hydrogen. So it's an HCl. Let's call it a molecule for now. We have any water around, that hydrogen is going to fall off. But let's say this is in gas phase so that it's not falling off. So we have an HCl molecule. Okay? So you follow me so far? Yes? All right. What can you tell me about polarity in this case? What does that word mean? What did it mean at the end of Gen Chem 1 when we talked about geometry and polarity? All right, let me ask a different question. How many of you got to in your Gen Chem 1, whenever it was, or wherever it was, how many of you got to the idea of molecular polarity? See, less than half, Allison, this is probably, we might need to do some catch back up. So help you figure out where they are and clarity. So y'all, it is a topic that is often, it's the right word here. It is often, it comes at the end of Gen Chem 1, and so a lot of times we don't have enough time left for it as we would like to have, right? So I think it kind of gets shorted a lot of times. So we definitely gonna need to review some molecular polarity. Let me see what I have left of this. I wonder if I need to go ahead and put it in. A lot left. What time is it? We only have 15 minutes left. I'm probably not gonna get done with this lecture today anyway. Thinking about going ahead and just making sure we reinforce it. Yeah, let's try to talk about, well, I've got some in here. Let me go to this. Trying to think how I want to do it. People are acting like they've not heard the ideas very much, so I don't want them to be up here talking for no good reason. Does that make any sense? So let's do this. Let's try. Did you hit those bright lights up here that I hate? So they'll highlight this middle. And we'll try to, yeah, we'll adjust it. So, all right. Hopefully this will be able to see. It's still recording. So let's talk about polarity. So, and I'm sorry, those of you that do feel like you're good on this, it's not going to hurt to review it. I want to talk about I'm going to talk about geometry first. Let's do methane, CH4. Let's do this? What's the naming on that, Allison? Single carbon ketone with dichloro substitution. I don't know what it's called. And then I'm trying to avoid two carbon strings just to make it easier here. All right. Thinking about this, please remember your Lewis structures, remember drawing the lines and all that kind of stuff. Yes, is that ringing a bell? You still draw a Lewis structure for these? Everybody put these three. I'm gonna take up about a half a page drawing these guys and talking about them, and then I'm gonna do another set for the bottom half of the page. It's gonna be like a little more precise on the polarity stuff. So we're gonna talk about the geometry and polarity of these guys first. Can you draw a Lewis structure for each of those three? I would expect you to be able to after Gen Chem. Tell me where would y'all like to start drawing? Do you have a process for drawing Lewis structures?
Me?
Yes.
Like on the first one, what I did,
Yes.
put the C in the middle.
Okay, wait. So yes, she's right to put C in the middle, and the way we decide that is we look for the least electronegative. However, we have to make a caveat here and say the least electronegative, not hydrogen, because hydrogen can only have one bond to it as far as y'all are concerned. So I have to end up good with carbon in the middle. I got carbon in the middle. Something else I would have liked to have done before that. What? Yes? Oh, how many electrons do I get to use? Hey, how many bonding electrons or valence electrons are in this system? Hydrogen brings how many? One each, right? 4 of them, so 4 total, that's 4. How many valence electrons does carbon have, and how do I tell it? How many? 4. Okay, so I've got 4 from carbon, 1 from each hydrogen. How many total bonding electrons do I have here? 8 bonding electrons, right? I like to list it to keep track because we're gonna do some that are a lot more complicated that's not so easy to just see. I know you just see this. Okay, then I've got your carbon up here. What should I do next? Wow, been a long time since 61? All right, lay everything else out. Draw single bonds to everybody like this. Each of those single bonds represents 2 electrons. Therefore, drawing 4 single bonds used up how many of my electrons?
8.
Oh, well, okay, then I'm done, right?
Great.
All right, so that's my structure. Yes? Yes? All right, let's do it for the dichloro compound in the middle. Let's figure out first how many valence electrons do I have? How many do you see? Oh, yeah, let's see. 4 plus 14 is 18 plus 6, 24. I agree with her. I agree with her entirely. 24. Y'all see how she got 24? If you do not, you need to practice these. Okay? What would you like to do to start with now? Something she wanted to do to start with, but now our decisions have a few more pieces. What's going to be my central atom? Here, Lord. C is, how did you spell that? Let's see, I'm looking at this, or this. Which one's least electronegative? Now, I know I don't have electronegativity numbers up here. The easy thing to look at is how far is it from fluorine? The further that way or that way, the less electronegative. Okay? Put carbon in the middle. Good, Lori. All right. What else would you like to do? What's next? What do we do over here? Attach everything. Okay, I'm gonna attach everything. You ready? So I've got. Okay, yes? Is that happy?
No.
Wait, one. Oh, we've not used them all yet, but for now, for this step, how many electrons have I used so far?
6.
6. Okay, so now leaves me 18. All right, now my next step is to do what? And this one you might not be thinking of. What's my next step? Say again? No, you're skipping steps. It will have eventually, you're right. But we got to sneak up on that process. Yeah, well, so fill up all my outer electrons now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yay, now I used up all my electrons. Good, but now I'm gonna go to what you were talking about. So what he's doing is he's checking everybody to see if they ever have full on text. Is this guy's fluorine here, does it get to see 8 electrons? 6 in 3 lone pairs, plus 2 in one of the bonds? That's 8. Good, it's happy, this is happy. But carbon doesn't because it only sees how many? 6. Oxygen sees 8. So it would be happy, the carbon's just not happy, right? So now your trick was to, right? Pull those over there and make the double bond, you said. Yes? Okay, good. Good so far. All right, last one, CO2. What do we need to do for that one? Walk me through it real quick here. How many electrons? 16, all right. Then do what? Carbon in the middle. Then attach the oxygens. How many did I use? Leaving. Okay. Then both the outer. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Okay, good. We're down to 0. Now what? Why? Oh, what do you want to do? Yeah, we're going to pull from both sides, right? And end up with, yes, happiness? All right, good. So now we have Lewis structures for everybody, right? I know better. So now we have Lewis structures for everybody. You can tell me the molecular geometry and polarity for each of those molecules, yes?
Yeah.
Good. Can you? What? Tell me which one, tell me. What is the molecular geometry for this guy? I agree with that. Yes, you follow? What is the molecular geometry for this guy? Okay, all right, is this one easier? What's the molecular geometry for this guy? Yes, louder, Miriam. Huh? It is indeed tetrahedral. This one's tetrahedral. This one's linear, leaving, get close. Trigonal plane. Yes. All right. Trigonal plane. All right, cool. So now we've got their shape, their molecular geometries. Which of these molecules is polar? All right, let me do this. I'll help you can. Okay. I'm going to ask you 1, 2, or 3. No, 0, 1, 2, or 3. How many of you vote that 0 of these molecules is polar? How many of you think 1 of these molecules is polar? How many of you think that 2 of these molecules is polar? All right. And how many of you think all 3 of them are polar? Okay. What do you think, Allison? I think I'm going to go with. You go with 1? All right. All right, let's talk about it. Why would you say that? Pick one and tell me why you would say it is. Which one do you think it is, polar or non-polar? Yeah, your choice. You get a choice of all 3 of them, and you can pick either direction. What do you think? Okay, that's fine. There are a lot of electrons. Okay, keep going. You think it's polar or non-polar? You think it's polar? Okay. So same one with a different interpretation or a different one? Big one. You said the middle one is. Oh, okay. Because why? Can you give me a more reason, or am I going to make you pick a different
The
molecule?
negativity between that.
Oh, okay. Now we're going to get deeper. He's going to say there's a significant difference in electronegativity between chlorine and carbon, between oxygen and carbon. That's going to be our key, and we're going to have what are called polar bonds, right? If that's going to be a key, do you think it's polar or not? The middle.
It is.
It is, okay. You want to pick one? No? Want to pick one other? Pick another one for me. First one or the last one? Methane. We're over time, y'all. But methane, I am going to claim, y'all, that methane is not polar. We can lean into your definition of just saying that they don't have significant electronegativity differences. That works for now. It may not work when we come back. However, this one, carbon and oxygen do, in fact, have a significant difference in electronegativity. However, I'm going to claim this molecule is not polar, and I need you to go look, remember why. Okay? Yes. You can have it. It's
I think that's like
Vector, the problem is that we usually don't actually tell you about the magnitude of those vectors.
I don't know.
But what you care about is magnitude of those vectors, same, not same. Okay? All right. Help me remember where I stopped, so we can pick it up on Wednesday.